रे अछि रे बर्तन माने ऑनलाइन. So in our previous class we have discussed with the paging technique. Basically memory has two different ways the program is stored in memory. One is contiguous memory allocation, another is non-contiguous memory allocation. In contiguous memory allocation, the program is stored in contiguous locations, and they are of we have read about fixed number of equal size fixed number of partitions, variable size partitions, and dynamic partitions. For continuous non-contiguous allocation, we have read about one of the technique called paging, where the program is divided into pages and the memory is divided into frames, and program may not be stored in continuous memory location. We have a TLB also, that concept we have read, which stores the frequently accessed pages information. There is another technique which is being used for storing, which is being non-contiguous memory allocation. So unlike paging, where the program is divided into pages, in segmentation, the program will be divided into some, some segments. What is a segment? Segment is a individual block, maybe a function, maybe a stack, a program itself, the symbol table, they can be one segment. One subroutine can be a segment. In paging technique, we divide the program into pages, fixed size pages. Here we divide the program into segments. Segments may not be of equal size. Segments are not of equal size. Correct? What can be a segment? Any individual block. Maybe function, program, procedure, method, object. This can be one segment. So segment more related to the logical view or programmer's view, whereas paging is a task by the operating system which decide that what is the page size. So this is your logical address, which is divided into some segments over here. That is being divided into some segments. Correct? Now these segments which are there in the user space, we said these are the segments. This segment will be loaded into memory. The segment 1 may be loaded into one other memory location, 2 may be some other location, 3 may be so they may not be in contiguous locations. However, one segment will be stored in one continuous location. Segment 1 may be about 100K, 2 may be 50K, 3 may be 500K, or 4 may be 200K. So different segments are of different sizes, and they will be loaded into the memory, right? So in this case, the processor generates the address which has two parts, segment number and offset. In paging technique, the processor generates an address which have two types, page number and offset. Here in the segmentation, processor generates an address which has two parts, segment number and offset. So segment number, what is being generated in search in a table called segment map table. Like in your paging, you have a page map table. Now you will also have a segment map table, which will be searched. In paging, user specifies a single address which is partitioned by a hardware into a page number and offset. Similarly, here we have segment number and offset, but in the segment table, we have two things over here, base and limit. Base and limit. In page map table, what is there? Only the frame number. What we are keeping over here? Base and limit. Suppose this segment 1 is loaded over here. What is the base and what is the limit? Segment 3 is loaded over here. What is the base and what is the limit? So every segment, for every segment, we will keep the base and limit. The starting address of this table is stored in a register called segment table base register. This is exactly same as the page table base register, PTBR. So there PTBR stores the starting address of the page map table. Here STBR or segment table base register stores the address of the first location of the segment table. And the length of the table is stored in STLR, segment table length register. Is it understood? we have a table called segment table, which has two entries, base and limit. For every segment, there is a base and limit. Processor generate an address which has two things. One is segment number, second one is offset. Starting address of the segment table is stored in STBR. Just see over here. This is the segment table. This is the segment table. Correct? Now, this has base and limit. Two things are there. For every segment, there is a base and limit. CPU generates the address known as logical address. The logical address has two parts, segment number and displacement. This has two parts, segment number and displacement. So just see over here. This address is known as which address? This is the logical address generated by the processor. This segment number is compared with this, suppose segment number 3. So it goes to 3. Third entry in the segment table. Is it understood? The segment number, suppose segment number is 3, it goes to the third entry. From which, from third entry, what it will get? It will get base and it will also get limit. Correct? So it will check that whether it is less than this limit or not, because it should not generate an address beyond the limit. If the limit is 100, then it should be the, whatever we have, the displacement must be less than that limit. So this limit must be compared with the displacement. With the displacement, it is being compared. This is displacement compared with this limit. Is that clear? Displacement compared with this limit. If it is less, then it is added with the base to get the physical address. To get the physical address in the memory. If D is not less than L, then it is error. Is that understood? Because in the memory, wherever the process may be stored, suppose this is the segment. This segment may have a starting address which is in the base, and maybe it is spanning over 700. That means limit is 600. If limit is 600, it must generate an address between 0 to 599. Is it or not? Because the limit is 600, any address must be generated from 0 to 599, which must be added with this base to get the physical address. So this address, which is the displacement, any address between this, should be less than this limit. What is limit? Limit is 600. In our case, the limit is 600. So this displacement must be less than this limit. If it is less than, then it will be added with this base to get the physical address. Is it understood or any doubt? Any doubt from this slide? This is important. This architecture, this hardware is important for segmentation hardware. Okay. So now,
No, sir.
okay. So now this is being added with the base. Once it is generated, suppose it must generate between 0 to 599. If it is generating 200, 200 will be added with this 100 to get this 300 as the physical address. Just look into this example. We have how many segments? 0, 1, 2, 3, 4, 5 segments are over here. We have 5 segments in this example. Subroutine, stack, symbol table like this. For each segment, for segment 0, what is the base? For segment 0, the base is 1400. See over here. For segment 0, this is for segment 0. For segment 0, base is 1400, limit is 1000. For segment 1, it is 6300, limit is 400. For the segment 2, the base is 4300, limit is 400. For the next one, for the segment 3, the starting is 3200 and so like that for every segment, the base and limit is given. And where it is stored? This is stored over here. Segment 0 is stored over here. Segment 1 over here, segment 2, segment 3, like that it is being stored, and segment 4 is being stored in the memory, right? This is being stored. Now, wherever any address, suppose segment 2 generates a address 430. For segment 2, it generates 430. Is it a valid address or not? For segment 2, it generates address 430. The displacement is 430. Is it valid or invalid? 430 is valid or invalid? For segment 2, I am saying.
Invalid.
Invalid, because its maximum range is 400. It cannot exceed 400. So if it generates 200, then 200 is valid. It will be added with 4300 to get the physical address. So computation is done in that way. So therefore, this memory is being protected. It is written that one of the advantages of segmentation is association of protection with the segments. Protection is more natural at the logical level, such as sharing common procedures rather than sharing a fixed page. So in paging technique, the program is divided into pages. So if I want to share a program, that means I have to share many pages. But if I want to share this subroutine, I just have to share a particular segment only, right? A particular segment I may have to share. I just want to share 1400 to limit is 1000. This only I want to share. But in paging, it would have been stored in 2 or 3 different memory locations, which I need to share. So sharing is what? Flexible is in segmentation. So in memory, there will be some segments which contains only program instruction and some segments only data. So if you want to share data, you just need to share those set of addresses. Correct? Okay. Now, the drawback of the segmentation. Using segmentation, it is more difficult to manage memory because we have to search a proper hole. Because segment, as a segment, a particular segment has to be stored in a continuous location. So we have to search for a particular hole or a appropriate hole where a particular segment can be kept. So therefore, it may cause external fragmentation. Correct? So therefore, segmentation may cause external fragmentation. Correct? So if the average segment size is small, external fragmentation will also be small. So this one of the example is putting suitcases in car dicky or versus putting individual items in a car. If you try to put a entire suitcase into the car dicky, it may not fit, but you open it and try to put all these items in the car dicky, it may fit into the car, right? Let us take an example over here. Similar examples may come in your exam. What is given over here? Consider the following segment. This segment has base address this and the limit is given. For every segment, the base and limit are given. Correct? This is the base and limit are given. What are the physical address of the following logical address? Suppose a logical address is generated 0430. That means for segment 0, the address is 430. First we'll say for segment 0. For segment 0, what is the base? What is the length? 600. What is generated? 430. 430 is less than 600. That means it is valid. If it is valid, it will be added with this 219. So 219 for 430, it is 649. Correct? Is it understood or not? Suppose the address generated for segment 1, the address generated is 10. For segment 1, what is my length? 14. What is generated? 10. So for 10 is less than 14. So therefore it is valid. Now 10 will be added with 2300 to make the to compute the physical address. Look at the next one. For segment 2, it generates 500. What is segment 2? What is the length? The length is 100 and it is generating 500. That means this is a invalid call. to the invalid access to the memory. So this will have this is a trap to the operating system. Understood? And for the next one, 400 for segment 400 is less than 580, so it is valid. So you add with 1327 to get the physical address. Then it generates 112. It generates 112, whereas the limit is 96. So you are generating beyond the range. So therefore it is an error. I hope it is understood. Can you compute or not? Very simple. Just compare the displacement with the length. It must be less. If it is less, it will be added with the base. Is that clear?
Yes, sir.
Okay. So usually a question comes that what is the difference between paging and segmentation? Some of the differences already you have marked. In paging, we divide into pages, where in segmentation, we divide into segments. Segments may be of different sizes, pages are of fixed sizes. In paging, we processor generates address is of process is the page number and displacement. In segmentation, we generate an address called segment number and displacement. In paging, we use a table called page map table. Here we use a segment map table. In paging, general external fragmentation doesn't occur, but in segmentation, external fragmentation may occur, right? This line is actually written correctly. It suffers from external fragmentation, right? And this may suffer from internal fragmentation. This line is written correctly. Paging is faster than segmentation. Paging is faster than segmentation. And operating system is responsible for this page size, where segmentation compiler is responsible, means more on the user, and this is for the operating system. I think this much 5 to 6 differences is easily you could able to write. Can you write or not? Say paging and segmentation is usually comes as a difference. Okay. Now we have read two things for non-contiguous memory allocation. One technique is paging, second technique is segmentation. Now the third one is a combination of these two. It says segmented paging or paging with segmentation. We said paging with segmentation or segmented paging. Just look over here in my previous example of segmentation. In segmentation, the program is divided into what? Segments. And we have a segment map table, segment table. It says that the segment will first divide into segment, then again segment will be divided into pages. Try to understand. In this paging is what? Program is divided into pages. Now we'll divide each segment. We'll take one segment as one program and we divide it into pages. Correct? So that it will be divided into a fixed number of pages only. Now for every segment, we'll have a page map table. For every segment, we'll have a page map table. So program, just look over here. Each of the segment will divide into what? Some pages. Because we know that paging is faster. So therefore, we will divide the segment into number of pages, fixed number of pages, maybe 5. This is 7, this is 5, but the page size has to be set. Now what we'll do, from segment 0, I'll reach over here, and from this, I'll have a PMT for this one. So I may have a page map table. I may have a page map table for process for this segment 0, and for this one, I may have another table, PMT 1. Therefore, for every segment, I will have separate what? Page map table. So what we have done, we have page each of the segments. So we say segmentation with paging. That we are going to do. Segment with paging. Now, the processor will generate an address which have 3 things: segment number, page number, and page offset. That means first we'll use the first part is the segment number. From the segment number, this is the segment number from which we go to the segment table. Segment table will have segment 0, segment 1, segment 2, like that it is there. Suppose segment number 2. So it will reach on the 2, this entry. It will go to this entry. Now from this entry, I will go to a what? Page map table. I'll go to the corresponding page map table. I'll go to PMT2. Correct? In PMT2, I'll have again some entry. So which one I'll go for? I have another entry over here is the page number. I'll have another entry over here, page number. So from here I will get the corresponding page number, and from this I will get in the physical memory where it is stored. And from this, to get a particular location, I'll use this offset or displacement. I'll use the displacement. I hope it is understood. So now processor generates the logical address. The processor generates the logical address, which have 3 parts: segment number, page number, and displacement. Using segment number, it is searched in the segment map table or segment table. From the segment table, a corresponding entry it goes to the PMT page map table. From PMT, it uses the displacement to get the physical address. Just see over here. This is the segment. This is the segment table. Right? For segment table, you have entry, page table entry are there. So from a particular, it will go to a particular page table entry. Right? So all these entry, the page table entry 1, page table entry 2, page table entry 3, number of entry are there. And this corresponds to page 1, 2, 3 of the segment 2 only. Because segment 2 is divided into number of pages, page 1, page 2, page 3, like that it's divided. These are the page 1, page 2, page 3 of segment 2. So that from a particular, I will go to a particular page, and from page I will get the corresponding entry in the memory. Is it understood? Is it understood or not? Segmentation with paging, is that understood? We divide the program into segments. Segment is divided into pages, and from which we use the displacement and get the memory address. Just see over here. Translation of logical address to physical address. Logical address means generated by the CPU. Physical address is actual address in the memory. Correct? So the segment number and segment offset is generated. So it goes to the segment number and page table base register, page table address. So it will go over here to the page table base. Page number, it will get from this entry, it will get the page table address. So that a corresponding frame number it will get. Frame number will added with this page table offset to get the physical address. So we have segment number, segment offset, and page number and page offset. I hope it is understood. Is it understood or not? So these are the advantages of segmented paging. Because we are taking the advantages of both paging and segmentation, so it reduces the memory use. Page table size is limited by the segment size. Segment table has only one entry corresponding to one actual segment, because in segment table, for every segment there is one entry, and for one segment I may have a multiple number of pages which will have one page table again. So external fragmentation doesn't occur, and it simplifies the memory allocation. And what is the disadvantages? Internal fragmentation may occur because we are using the paging over here. So internal fragmentation may occur. the complexity level will be much higher as compared to the paging. The complexity increases. Why is there? Because we have many computations. We go for segment table, we search in the PMT, we add the displacement, so complexity increases. And these page tables need to be continuously stored in memory. And these pages, page tables, suppose I have 5 segments and 5 tables are there, the 5 tables has to be stored in the memory. Is that clear? Is it understood or not? We have completed this part up to this part. However, this is being left for you for only the overlay is being left for you for self-reading. All other things we have for computed. Overlay is very easy concepts. You can read of your own. So this part is completed. Now we have left with this virtual memory concept. That is also important. In this virtual memory, we have, you might have read, I do not know whether you have read this page replacement algorithms, entire virtual memory. I think you must have read in your computer organization and architecture. But anyway, we'll cover it over here, the virtual memory. For module 5, we said architecture, the IO system, polling, interrupt, DMA, this is for self-reading. This part is for self-reading. Correct? And we'll have discussion on these problems and all. So anyway, so we'll go for the virtual memory. As assuming that you must have you read the virtual memory or not in computer organization? Have you read? Hello? Have you read the virtual memory in COA? Hello? So accordingly, I will teach whether if you have read it before, I'll just go through all those very quickly. Otherwise, I have to go in detail of these virtual memory concepts. This was there in computer organization and architecture. Hello? Hello? Can you hear me or not?
Yes, sir.
Yes, sir.
Then whether you have read the virtual memory in COA, a part of this must have been read. Anyway, so quickly going through this with the concept of virtual memory. When this concept of virtual memory will come into mind, whenever, suppose I want to execute a program beyond the main memory size. I have a memory of 4 GB. I want to execute a program of 5 GB. Now question is that whether I can execute or not. Okay. So whenever the memory size is is less than the program that I want to execute, then how to execute that program? So we may not be requiring all the 10 stages in a game at the same time. While it's playing in stage 1, if you complete stage 1, then stage 1 program is not required. We may take it out to the disk and stage 2 may be loaded into the memory. So in this way, we could able to play the game which is beyond the main memory size, because we may not be requiring the entire program to be loaded at the same time, right? So here only the concept of virtual memory came into picture. So program would no longer be constrained by the amount of physical memory that is available. So we do not depend on only on the what is physical memory available. We may execute a program beyond the main memory size. So it is a technique. So look over here, virtual memory is just a technique. It is not a memory that is present on your machine, like your cache memory or main memory is being present as a hardware. Virtual memory is not like that. It is just a technique that allows the execution of process that are not completely fit into the memory. So here the logical address is much larger than the physical address space. So it will allow to execute a program which has beyond the main memory size, because main memory size is the physical address, and no, I want to execute a program beyond that space. So the virtual address space is logical view of how process is stored in memory. Usually start at address 0 and continuous address until end of the space. Physical memory is organized into frames. Memory management would must map logical to physical. So what you have? This is my physical memory or actual memory. This is my actual main memory. Correct? So my program may be stored on a disk. Program may be stored on a disk. This is the disk. Disk capacity is quite more as compared to your main memory, and the program is stored inside the disk. The program may be stored over here. Correct? Now this program, I am not loading the entire program into memory. The main memory will be divided into frames. The program will also be divided into pages, like the paging technique, and this will be loaded to the memory, and whenever not required, it will be taken back to the disk. And what is this process called? I have already told. This is called swap in, and this is called swap out. This is called roll in and roll out. If you are taking out of the memory, roll out or swap out. If you are bringing to the memory, we say swap in or roll in. So this can be implemented two ways. One is demand paging and demand segmentations. Demand paging means, demand paging short definition is a page will not be loaded to the memory unless and until it is being demanded. Correct? I repeat it. A page will not be loaded to the memory. A page will not be loaded to the memory unless and until it is being demanded. Suppose if the page 0 is not being demanded, I will not load into the memory. If it is demanded, then only I will load. If page 3 is requested, then only I will load. Correct? So it is not that I will load the entire program into the memory. I will not load the entire program into the memory. I will load whichever is required or demanded at the time. Similarly for the demand segmentation, right? Whichever the segment is required or is being the processor demands, at that time it will be loaded. Just see over here. This is physical memory. I have a virtual memory. You can see over here, this virtual memory is quite large as compared to this physical memory. So pages are being mapped into this physical memory. So I cannot keep all the pages in the frame, but if I bring a page where I will keep, that mapping is over there. That mapping is over here. If I bring page 0, where I will keep? If page 1, where to keep? I am not keeping all the pages at a time, but where to keep that mapping is over here. The memory management unit is responsible for this mapping. The memory management unit is responsible for this mapping. Correct? I hope this diagram is understood. The virtual memory or the program is quite less as compared to the physical memory. So we cannot keep all the pages of the program into the main memory. But if it will be, if a particular page will be brought, where to keep that information is there in a table. It's a memory map over there. So virtual address space of a process refers to logical view of how a process is stored in memory. Virtual address space means processor now generates an address beyond the main memory size. It is now not restricted to the physical memory. If you are using virtual memory, then the processor can generate address beyond the main memory size. So usually design logical address space for stack to start maximum logical address and grow down while heaping. So just look over here. So this is the code, data, and the heap area. This is the stack, your array, function, all these are stored over here. The dynamic memory allocation and all these are being done in this heap area. Usually design logical address space for stack to start at max logical. So from here it is the stack grows, right? The stack grows down, logical address and grows down, while heap area grows up. You can see this arrow. The heap memory area goes up, while the stack grows in the downward direction. Correct? So every time you are allocating memory or something, dynamic memory allocating the memory, the heap grows in this way, whereas the stack grows in down this area. So you have some of the library that you may want to share by multiple processes. This is for this shared library are being stored in shared pages, and this address space and is, you can see over here, by two processes this can be shared. It will be shared in a location, the address will be shared by two different processes. So coming to the demand paging, this is important. As I said, demand paging is what? Page will not be loaded to the memory unless and until it is being demanded. So could bring entire process into main memory at load time. We could bring, but or bring a page into memory only when it is needed. There are one thing, I can bring the entire program, or I will bring a page when it is required. Then if I bring only a page when it is required, then less IO is needed, less memory needed, faster response, and some more users can be satisfied. These are the advantages we get if you go for demand paging. Correct? So similar to paging system with swapping. So now this is nothing but the paging technique, but with swapping, means we are taking out something to the disk as well. So instead of swapping a process into memory, swaps a page into memory when it is demanded. Therefore, this is known as lazy swapper. This is known as lazy swapper. This comes as a short question. What do you mean by a lazy swapper? The lazy swapper is nothing but the demand paging. The page will not be loaded unless it is being demanded. Therefore, this is called lazy. Never swaps a page into memory unless page will be needed. Is it understood? What is lazy swapper? This is very, very important. Lazy swapper is nothing but the demand paging. Because why it is called lazy? Because it is not loading everything. It is loading whenever somebody instructs that you load this page. So program load is stored over here. So this is the program. This is taken out and another part is being loaded over here. You can see over here, this is a new program is loaded and a part program B is loaded, where the program A is taken out, swap out. So with swapping pager, what is a pager? Pager is a swapper that deals with pages is called a pager. So the swapper which deals with these pages is called a pager. So in swapping, pager guesses which page will be used before swapping out again. So instead, pager brings it in only those pages in the memory. So which pages will be brought? Which will be in use. So therefore, this decreases the swap time and amount of memory just by looking into that which page will be required. Now we'll say that how will you know that which page will be required? So it make a guess. Guess is not a random guess, rather an algorithm is being formed. Through that algorithm, it will guess that which which page will be in use, and that will be brought into memory, so that time lost for searching can be saved. To know which page in memory and which is in the disk, each page table entry is a valid invalid bit. So a valid invalid bit is associated with each of the frame that we have read it earlier. In page map table, we have entry of frame number. Along with that, for every frame, there is a bit associated is called the valid bit. This bit is set to 0 or 1 or valid or invalid. Correct? So if it is 1, that it means it is valid, 0 is suppose invalid. So if it is present, V is in memory, memory resident and legal, I is not in memory or in the disk and it is invalid. I means it is not in the disk. Is it understood? So that means whenever it is brought, it will be changed to V. Is that clear? One more concept over here is called the page fault. What do you mean by page fault? If a particular page which is being searched is not found in the memory, then we say a page fault occurred. If the referenced page is not found in the memory, we say a page fault occurred. If a page fault will occur, what will happen? We have to bring it again from the memory, from the disk. If it is not present in the memory, that means it is there in the disk, I have to bring it. So if it is not found, it is page fault. Can anyone say that suppose no program is there in the memory? Whenever the first I am starting a program, whether a page fault will occur at the first occurrence or not. When I want to execute the program, in the starting of the program, I want to execute the program, whether the page fault will occur or not in the demand paging. Anyone we can say? See, initially all are empty. Demand paging means page will be loaded when it is being demanded. When the processor will demand for page 1, it will not be found in the memory. That means page fault. Goes to the disk, bring it to the memory. Next time if page 1 is searched, it may not be a fault. This is the same thing that I have told. Is you can see over here, this is the logical memory where these are the pages. For each of these, the frame number, the page 0 is stored in frame 4. The page 0 is stored in frame 4, page 1, page 2 is in 6. So currently 0 to 5 pages are in memory. These are there in memory. Other pages are on the disk. You can see the other of the entire program is on the disk. The entire program is on the disk. But currently A, C and F are there in the memory. Correct? So therefore this is valid, and this is valid. All other are invalid initially. The bit is invalid for the other processes. Correct? If a page fault occur, then what happens? As I said, if a page fault occur, that means it is not found in the memory. So it has to brought from the disk. It has to brought from the disk. So operating system checks an internal table kept in PCB to decide whether the reference was valid or invalid. If it is valid, that means it is present. If it is invalid, it is not present. If the reference is invalid, it terminates the process. If it is valid, the OS brings the page into memory. Right? So similarly, we have this bit that we have, what is that we have set over here. We brought the memory and make it valid. To bring the page into memory, the OS first finds a free frame. For first, it will check that where the free frame is there or not. So free frame list is there. From there, it will check that which is the free frame, and schedule a disk operation to read the desired page into the newly allocated frame. So this procedure already I have told you that in simple, you remember that whenever a page fault occurs, the processor brings the page requested page from the disk, and set it to a valid page. The rest of the things we will read in the next class itself. Next class, the page replacement algorithm and other problems. So any doubt till now?
No, sir.
Yes.
Page fault occurs, then page fault occurs, then demand paging will start.
If the page fault occurs, then I could not hear. If the page fault occurs,
Then the demand paging means, demand
see,
paging will
demand paging is I am bringing a page whenever a processor is requesting. I am not bringing the entire program. Program has many pages, so I am bringing only that page which is being requested by the processor. So that is demand paging or lazy swapper we are saying. Now, suppose I am searching for a page and it is not found in the memory. If it is not found, means it has not brought into the memory earlier, must be in the disk. So I will bring it from the disk. Now, while bringing it to the disk, the memory may be full. Some program has to be taken out. So if it is taken out, is swap out, and what am I bringing is swap in. So, swap in, swap out may occur or not, but if a page fault occur, we bring a page from the disk. Achha, roll number 2, 3, 7, 8. 19, 20, 22, 25, 27, 30, 32, 37, 39, 43, 49, 73. Roll number 7 is present. Okay. So just reading out the roll numbers, absent roll numbers. Roll number 2, 3, 8,